Hello, good people. Welcome to video number 1 of Unit 6, at least the beginning of Unit 6 here. We will be working with approximating definite integrals, but also connecting them to accumulations of rates of change. And so we're going to start in video 1 pretty straightforward, talking about a situation that you may have encountered in 2 units ago, in Unit 4, with some motion situation. So when you read situation 1, it says, particle P is moving along a straight path with a constant velocity of 2 feet per second. So every second it's moving along 2 feet. The graph of Vp of t, the velocity of particle P at time t, is given above. What is the total distance of the particle traveled from time 0 to time t? All right, I'm looking at the graph. I'm thinking about the situation. It's giving me a starting and an ending point. On the graph, the t values are represented here 0 and here time 2. So this is talking about that particular interval of points. But the question is, how fast is this going? Well, I'm looking for the total distance. And I remember from my previous math classes or science classes that when I'm looking for distance, I'm always multiplying rate times time. So I'm multiplying how fast is something going times how long was it going for. So when I look at this situation, I know that the rate is 2 feet per second. 2 feet per second. And I'm going to multiply that times my time. How long was it in motion? Well, it was in motion from time 0 to time 2. And so I'm going to write it this way. 2 minus 0, which would just give us 2 seconds. But where did I get the 2 seconds? Well, I subtract my ending point minus my starting point. That's going to give me my time. Oh, well, when I multiply this yellow and purple value, I'm going to get 4. And if I look at the units, I'm dividing by seconds, I'm multiplying by seconds, so those are going to cancel out, and I'm left with feet. So the total distance traveled would be 4 feet. Now, you didn't need to this handy-dandy formula, right? Like you could have thought, well, in 1 second it moves 2 feet, in 2 seconds it moves 2 feet, so therefore in these 2 seconds it moved 4 feet. Right, or I think I misstated that. In the first second, it moved 2 feet. In the second second, it moved 2 feet. So 2 seconds, 4 feet, right? So I guess conceptually that makes sense. But here's what I want to focus on. This formula that I wrote in blue that produced the correct answer, really, if you focus on the graph, the rate is represented by the y-axis. And the time is represented by the x-axis. And what I'm doing is I'm multiplying this vertical axis times the horizontal axis. And that's producing my total distance. But if you do that, if I multiply this length times this length, well, then we really found the area here. And so this area under the curve which is really a horizontal line, and the horizontal line, which represents a rate of change, right? The velocity is a rate of change. What this is telling us is, if I find the area under this curve, I'm going to find the total distance traveled because I'm multiplying rate times time. Okay. How is this related to what we did in the previous set of notes? Well, in the previous set of notes, we were looking for definite integrals. And we said definite integrals are graphically represented by the area under the curve, right? The area that's trapped between the function and the x-axis. Now, that area could be positive, it's above the x-axis. That area could be negative if it's below the x-axis. But that's what the definite integral represents. And so what we're saying here is we found the total distance by taking the integral from 0 to 2, and I guess I'll do those in the color that I had highlighted them earlier, 0 to 2, of the velocity function. dt. Now, if you look carefully, this was my rate, and this is my time. And so when I do an integral, and I'm taking the integral of velocity with respect to time, these two symbols kind of remind me of this setup I did over here. And what I'm doing is I'm accumulating from 0 to 2 all of those areas, I guess, that go from 0 to 2. And that's how I can find the total distance. I say that because if my velocity function is not a straight line, and if it's a curve, I can still find the total distance by setting up my integral in a similar fashion. And I think that's what happens in example 2. Situation 2, there's another particle Q. It's moving along a straight path. However, its velocity is increasing. How do I know the velocity is increasing? Well, here's the velocity graph, and it's going up. So the velocity is increasing as it moves. The graph of v sub q of t is given above. What's the total distance of the particle from 0 to time 2? Well, now I have an issue because I have a curve in my graph. So I could do a couple of things. I could find some points that I know. For example, I definitely know this point. I think I know this point, and maybe I know this point. So I cannot find the area under the curve. What I could do, though, is I could find an approximation. I could find an approximation by creating like a ginormous trapezoid here. And if I find this area, that will approximate the area that I'm really looking for. And so I guess here's where I want to make the connection to situation 1. In this problem, just like in the other problem, I'm looking for the total distance. And I'm going to find the total distance, just like I did in the other problem, by taking the integral from my starting point to my ending point, which happened to be the same. And I'm going to find the total distance by multiplying the rate of change, which is the velocity, times time, which is going to be represented by this dt. And so therefore, this is what I need to find. But if I'm finding this, I'm really finding the area that's under the curve. So if I can figure out the exact space that's underneath this curved part from time 0 to time 2, I found the total distance. But what makes it a little bit more complicated is that this is not a perfect geometrical shape. It has that curve. So I drew this trapezoid as a way to help me approximate it. Here's what I know. At the very least, I know that the area that's under the curve cannot be more, has to be less than this yellow trapezoid. How do I find the area of a trapezoid? Oh, that's a good question. How do I find the area of a trapezoid? Area, wrong color. Area of the trapezoid is equal to, there's different ways you can do it. One way I remember it is take the average of the bases and multiply times the height. Now, I got to know where are the bases. In this four-sided shape, the bases are always parallel to each other. So this is base 1, and this is base 2, and I'm giving you the measurements based off of the function values of that curve. That means this is the height, and that height is 2. So be careful. I think a lot of students, if you turn your head like 90 degrees, oh, there's a trapezoid. That looks like more, I guess I'll draw it over here. This is maybe a more familiar trapezoid picture. And that's what we're looking at, except it's rotated, right? Oh, so I can figure out the area. So I can find the area of this trapezoid by taking the average of the bases and then multiplying that times the height. This is a 3, by the way. Add 1 and 3, you get 4. 4 divided by 2 is 2. And 2 times 2 is 4. Oh, hey, that's interesting. Oh, well, that's almost, well, whatever. We'll come back to that. So here I have the maximum. It has to be less than this. because the shaded region, there's this empty space that the orange trapezoid uses, and it has to be less than that. All right, so then can I find a lower bound? Well, I don't know how to draw another trapezoid to figure that out. So what I could do is I could draw a rectangle here and a rectangle here. And the areas of these rectangles are definitely less than the shaded region. So in yellow, I have the upper bound. In the red rectangle areas I'm about to find, I have the lower bound. How do I find the area of these rectangles? Well, there are two of them. So I'm going to do base times height. So that's 1 times 1. Plus, the next one's going to be base times height, 1 times 1.5, we'll say. Maybe I'll use parentheses, that way you can see. And then when I put those two together, I'm going to get 2.5. Okay, so now I guess I know that my area is somewhere between 2.5 and 4. 2.5 was too low, 4 was too high, so it's somewhere in between. Could I get an even better approximation? Maybe. What if, let's see if I can erase these red things. What if I drew more rectangles? What if I said, let me draw this rectangle. Let me do it half. My base is going to be half instead of 1. And what if I use this and get that rectangle, and use this and get that rectangle, and use this and get that rectangle? Hey, do you notice that the little spaces where I had this extra stuff went away? It got smaller? Like, it's getting smaller. The more rectangles I build, the smaller the leftover, I guess, that I'm lacking. So what this is pointing at is one of the ways that we're going to handle these situations where we have a curved function is we're going to use geometric shapes that we do know, like the trapezoid, like rectangles, because we can find the areas of those, especially because we can figure out the base by just finding the full length and dividing by however many rectangles I want. That's going to be the length of each base. And then the height is really just based on the y-coordinate of the curve at that particular x-coordinate that I'm calculated. So using rectangles and trapezoids, we're going to approximate these areas. We're not going to get the exact, but we can get pretty close. So here's key concept number 1. The area bounded by a rate function, if I'm given a derivative function, gives the accumulation of change of the original quantity. It can be positive if it's above, or negative if it's below. If we have nonlinear and non-geometric graphs, then we're going to need calculus. But we're going to use approximation methods to estimate these areas. The first of which is going to be something called the Riemann sum. And that is what we're going to do in the next video.